So what we said last week, so at the last moment, when we finished, so we constructed the gauge invariant states of the theory, and we said that the SU2 gauge invariant states are the spin network states. And we said that the spin network states, S, they are labeled by a graph embedded in the manifold by a collection of spins for all the links of the graph and a collection of intertwiners for all the nodes of the graph. So, for example, a simple graph is like this. So with two nodes. J1, J2, J2 and J3. And so since these states are gauge invariant, this means that the action of the quantum Gauss constraint on these states is zero. So it means that these states, they are in the kernel of the quantum Gauss constraint. So this means that the quantum Gauss constraint acting on these states is zero. And so this is by construction because we constructed, so we said that the action of G on a holonomy is the following. So it's G So what we said is that the action of an SU2 gauge transformation on a holonomy is just a discrete action at the endpoints of the holonomy. So this is the reason for which all we have to worry about when we study the SU2 gauge transformation is what happens at the nodes. So what happens at the starting point and the endpoints of the holonomies. So we can orient them if we want, but like this. So the only thing we say is that if you want the states to be gauge invariant, we have to impose some condition. So what happens at these nodes? What we said is that this condition is in fact easy. What we have to put at the nodes is not just any SU2 tensor that recouples representation, but we have to put invariant tensors. And these SU2 invariant tensors, they are called intertwiners. And so invariant means that, for example, if you have an intertwiner I alpha beta, it is acted upon by a representation matrix, for example, alpha beta. Or just its decision. So the action of the gauge transformation on these intertwiners is the intertwiner. Now we are already like halfway through the full quantization because we're able to find the states that solve the quantum SU2 Gauss constraint. And now, so the next thing to do is to worry about diffeomorphism, because we said that in the Hamiltonian theory we have three constraints. So we have the Gauss constraints that we turn into a quantum operator. Then we have the diffeomorphism constraint, and we have the scalar constraint. So for the moment we impose the Gauss constraint. So what we did is we started with the first kinematical Hilbert space, which doesn't know anything about these constraints. So this kinematical Hilbert space was a generic graph with any SU2 tensor at the nodes. Then we said, okay, now we impose the quantum Gauss constraint, and this amounts to considering these spin network states. So now we have to impose diffeomorphism invariance. And in fact, so to impose diffeomorphism invariant, the construction is a bit more complicated than imposing SU2 gauge invariance. And the reason is that the group of diffeomorphism is a non-compact group. So in a position, so as opposed to the group SU2, so SU2 gauge symmetry is a compact gauge symmetry, because SU2 is a compact group. But diffeomorphism is a non-compact symmetry. And so what happens usually when we impose that certain states are invariant under non-compact symmetry, what happens is that we are taken out of the original space in which we were. So this means that you can see this in a very simple example. For example, if you take the space of L2 functions over R. So if you take this space, with the usual Lebesgue measure on R. So you can take all these states that are like all the functions that are square integrable on R. But now if you impose that these functions be invariant under translations, this is obviously a non-compact symmetry. Translations, it's a non-compact symmetry that we can impose. Then the only states that are translational invariant are the constant functions. The only functions that are functions translations. So instead of all these functions, it's just the constant. But then a constant is not an element of the space anymore, because a constant is not square integral. This means that imposing the symmetry takes us out of the original space. So this just means that to impose diffeomorphism invariance, just the mathematical procedure that is involved is a bit more complicated than just doing what we did for the SU2 gauge in practice. But in fact, there is a well-defined way to do this, and I'm just going to give you the end result, because the mathematical construction you can find in the books or the papers, or it's just a technical point. What is more important is really the philosophy, what is going on and what is the end result. And you can memorize that what happens at the end of this construction. So the construction itself turns out to be well defined, but what happens at the end of the construction is something sort of natural and to be expected. So you can think that what we started with were like graphs that are embedded in the manifold, and in fact imposing diffeomorphism invariance means that we forget about the embedding of the graph. It means that we consider graphs that are just abstract and not anymore embedded in the manifold. So why we do this in fact? Why these states are solution to the diffeomorphism constraints? You can understand easily, because imagine that we have, for example, a link like this. Now we act on this link with the diffeomorphism. Then we act with the diffeomorphism by diffeomorphism of the graph. This is just going to move the link like this. It's just moving it. So finding like the kernel to the diffeomorphism constraint means that we're going to identify all the states that are defined on graphs related by diffeomorphism. So if you take, for example, this state and this state, so these two states are the same. This is what it means in fact. So in the SU2 gauge invariant level space, these states are not the same. So these states are orthogonal. So in the usual, so in this, for the kinematical unit product, this is 0. Because if you are not at the gauge, at the diffeomorphism invariant level, the priority states are different because they are defined on different graphs. And even if these graphs are related by diffeomorphism, so just starting the graph, for the theory, mathematically, these graphs are the same. So now just imposing diffeomorphism invariance means that we just identify all these graphs. So we say that these two graphs are the same. And so there's just one subtlety, is that now, so you see that obviously a graph that has different number of links, they cannot be related by a diffeomorphism, they are different. So the only thing we can do with the diffeomorphism is deform the graph, in fact. And so you can see that also what diffeomorphism cannot do is remove a nut on a graph. Because we have to remember that these graphs, they are defined, so not a two-dimensional manifold, but in a three-dimensional manifold. Because these are graphs in a three-dimensional space. And if you have a nut in three-dimensional space, there is no diffeomorphism that can undo the nut. So for example, what I mean is that, for example, you can take this graph here, you can take this loop like this, and you can do a diffeomorphism that is just doing, trying to draw it, just doing this. So see, I didn't create any nut here. I just took like this part here and I moved it up there. So the crossing here, so the link is going above this thing. So there is no nut involved here. So you can find a diffeomorphism that does this. So in the diffeomorphism invariant space, these two states are the same states, in fact. But there is no diffeomorphism. It's impossible to find a diffeomorphism that there's this that puts a knot. Yes, this is a nut, right? I have to find something more complicated, but above. Okay, so this is a knot. So there are many nuts that we can construct, or we can put them together. So I'm saying is that if there is a knot like this, for example, there is no way to do diffeomorphism and undo the knot and have something like two separate groups. So this means that at the diffeomorphism invariant level, what we consider is not just like an equivalence class of graphs, but an equivalence class of knotted graphs. You have to know if the graph has knots or not. So again, just
equivalent class of knots. You are considering equivalent class of?
Yeah, of knots, yeah.
Knots.
Yeah. Because diffeomorphism cannot take us outside of the knotted class. So this means that if we have like a knotted class, for example, a set of graphs or loops that have one knot, we can do all the diffeomorphism that we want. All the states are going to be in the same diffeomorphism invariant space, but we cannot undo this knot. So we cannot go out of this family of knotted graphs. For the same reason, if you consider this graph, we can do all the diffeomorphism that we want. We're never going to create a knot. So roughly speaking, what we can think is that once we go to the diffeomorphism invariant space, what we have is an equivalence class of graphs related by diffeomorphisms. And so this amounts to completely forgetting the embedding of the graph in the embedded manifold. We can just consider abstract graphs. It doesn't matter if the link is here or if the link is here, for example. These are the same graphs. So this means that what matters in the end is just what matters about the graph is not the embedding of the graph on the manifold. It's just the combinatoric structure of the graph. So what we need to know is just the number of links of the graph, the number of nodes, and the connectivity, how the links and the nodes are connected together. But really the position, the precise position of the links doesn't matter anymore because of this diffeomorphism invariance. So in some sense, this is just to say that you see that once we impose diffeomorphism invariance, we do not like create states that are completely different from these states. So in fact, we're going to be telling more like what the geometrical interpretation of these states are, but roughly speaking, the states are still the same. We just now forget about their embedding in the manifold. So we're still going to consider these p-network states now, but consider just abstract graphs. And so now what we can do is we can say a bit more about the geometric interpretation of this graph. So what we said is that if we have a little, if we have a surface, what we said is that we saw with the surface operator, the area operator, that the links, we can see them as being dual to little surface elements that have a little microscopic area proportional to the square root of j plus 1. So we can have a little surface here. So the area goes like square root of j3 plus 1. In fact, we can do the following construction. What we can do is, you saw that in some sense what we did is to take a graph. What we did is to take a graph like this. So I put 4 random nodes here. And what we did is we labeled the graph with certain data. What we labeled the graph with was like an SU2 group element on the links. So this is the holonomy of the connection along the link. So here we put an SU2 group element on the link. And we also put like a flux element, an element of the Lie algebra on the link. And so this flux element is just a flux going through any surface dual to the link. So you can think that, so you have to think of these graphs not as being like physical objects in the manifold, because we have a three-dimensional manifold, and these graphs are not, this link is not like any link of geometry or a particle or anything like this. It's just a way in the manifold to represent, to mathematically write down the states. It's just a convenient way to draw a state from the geometrical or mathematical point of view. But it doesn't really correspond to anything. What does really correspond to something is the geometry that is, in some sense, that I'm going to tell you, dual to the graph. And what is this duality? The duality is precisely this one. You see that if you have if you compute the surface operator, we said that this link carries a little quanta of surface, a quanta of area proportional to square root of j plus 1. So this means that these links, you can see them as being dual to surface elements. And so the meaning of this is the following, is that once we label the graph like we did with elements of the group and of the Lie algebra, in fact, since we have this is an element of the group, and this is an element of the Lie algebra, it turns out that this data together, this gives a parameterization of the space, which is the cotangent bundle to the group SU2. Because I think, as I said last time, the group SU2 is a Lie group, it's a group manifold. And so as a group manifold, it has a cotangent bundle. So we can construct T star of SU2, so the cotangent bundle to the group manifold SU2, and this cotangent bundle turns out to be parameterized by the group element, and a Lie algebra element. So this means that if you give me a group element and a Lie algebra element, you're giving me a point in the cotangent bundle to SU2. So for the moment, we don't really see the geometrical meaning of this. But now, the way to see the geometrical meaning is to use a different parameterization. So it was shown by Faidal and Special. That these structures, instead of giving the data a group element in SU2 and a Lie algebra element in little SU2, you can give a completely equivalent set of data, so completely equivalent to this, but valued in slightly different structures. So valued in R times S1 and S2 times S2. I'm going to tell you what this represents. So this means that so this parameterization, you give an element, so a real number, an element of S1, an angle, and a normal in S2, a normal in S2. And what this represents geometrically is much more transparent than this. Geometrically, we don't really know. We have holonomies of the connection and fluxes of the electric field, so we don't really know. We sort of lost the link with the geometry of gravity that we started with. Sort of lost, like, what is the interpretation of this? Geometrically, what does it mean to draw this graph? So if you use this parameterization, it turns out to be a bit more transparent. Because, so this group had this real number that we call it J, this angle that we call it alpha, and then there is a normal M, and a normal M tilde. And the interpretation turns out to be the following. So now imagine that at each of the nodes here of the graph, you can put a tetrahedron like this. You see that on purpose, I choose a graph that is 4-valent. So the nodes are 4-valent, there are 4 links, because the tetrahedron has 4 faces. So in this sense, I was telling you that the graph is dual to geometry, to discrete geometry. It's precisely in the following sense. You can think of the node as being dual to a tetrahedron. So the node sits at the center of a tetrahedron, and the links describe the faces of the tetrahedron. So you see that, of course, I can take a three-dimensional manifold, and then I can triangulate the three-dimensional manifold. I can cut the manifold into elementary pieces. So, for example, for a 2D manifold, so if the blackboard is a 2D manifold, I can discretize the blackboard, the 2D manifold, by little triangles, for example. We can use triangles like this and discretize the blackboard. Of course, we can also use squares instead of triangles. We can do this, it's completely equivalent. So now this is really something physical. This is a discretization of the manifold. And so you see that now the graph that we're working with, what I'm telling you is that the graphs are just a convenient way or a dual representation of this discretization. In which sense? In the following sense. So at the center of all the triangles, I put a node of the graph. I put a node. Here I put a node, a node, a node. And then I connect the nodes by links. Maybe there's another link here, another one here. So I have this graph in black, I have this graph structure again. So these graphs are exactly the graphs that we used in loop quantum gravity, the graphs on which we define the states. So in this sense, once we know a graph, we know the discrete geometry dual to the graph. So here it would be the same thing. So you see that the valency of the nodes changes. If I put triangles, the nodes are all 3 valent. If I put squares, the nodes are all 4 valent. So we have the same thing here. We have a graph. And so now for a 3D manifold, the same thing happens, but instead of using triangles, I can use tetrahedrons. Or instead of using squares, I can use little cubes. So 3-dimensional cells. So for a 3D manifold, I can use a tetrahedron like this. And so what we're saying is that we can just go to a dual representation. It's just more convenient geometrically to represent these objects. Instead of writing down this 3-dimensional stuff, so we just put like a node that corresponds to the tetrahedron and then 4 links that correspond to the triangle. And so indeed, with this parameterization, so what J corresponds to the area of the triangles dual to this link. So this link is dual to this triangle of the tetrahedron. So the area of this triangle is J. And so the area of this triangle is also J. And now what this n and n tilde correspond to, this n corresponds to the normal to this triangle as seen from the two nodes. So this triangle here has one normal n, and this other triangle here has another normal n tilde. And it's even stronger than this. We can show that in this parameterization, you can show that these two angles, these two normals, sorry, n and n tilde, they're related by a transformation. And what is this transformation? It's just the SU2 transformation living on this link. So we have this group element, this SU2 group element on the link, and this SU2 group element is precisely the one that takes this normal to this normal here. And so essentially this angle alpha is related to the angle between the two normals.
What is the surface of the second one?
Sorry?
What is the surface of the second one? What is the area?
So now the area of this triangle is given by the spin of this thing. The area of this triangle is given by the spin of this thing.
What's the equivalent of the J? You have J of the area.
Oh, this J is also the same. So the two triangles that share this, that are dual to this
yeah,
thing,
they
have the same area. So this means that if you want, instead there is a discrete geometry encoded in these spin network states. So what we're sort of unraveling now is, I'm showing you that what we're doing is something rather natural, because we started with the phase space of gravity, then this canonical quantization, and we introduced these strange volumes and fluxes to this quantum construction, And then we have these weird states, we draw the graphs, and we say that there are intertwiners here and group representation. So it seems really strange. We don't know what this means from the point of view of classical geometry, what these graphs mean. So these graphs, they are essentially just a quantization, a fuzzy version of these discrete geometries. You can think exactly in this sense of the graph as being dual to discretized manifolds. So we see that now if we were able to mathematically take a sum over all the graphs, or graphs that are very fine, many nodes and many links, we would take the manifold to be, with the triangulation, arbitrarily small. We can refine now this triangulation. We can take it very small, put more triangles here. We can refine it. So if we refine the triangulation, the graph becomes just more complex. The graph has more nodes and more links and becomes much more complex. But for simple graphs like this, you can really think of this duality. And so remember that we said that on the graph, the Hilbert space of loop quantum gravity was an L2 space over SU2 to the number of links divided by SU2 to the number of nodes. And so this is SU2 to the L because on all the links we put the configuration variables, so the globalities of the connection, and divided by SU2 to the N because we look for the gauge invariant space. And what we just saw is that what is gauge invariance doing, or gauge transformation? The gauge transformation is acting at the nodes. So if I want to have the gauge invariant space, I divide at all the nodes by the gauge group SU2. So I take SU2 on all the links, and at all the nodes, I divide by the gauge group SU2. And this L2 space is the Hilbert space of loop quantum gravity on our graph. So this L2 space is just a quantization of this symplectic manifold. This you can think of this as being really a classical manifold, classical group manifold. So its quantization is this Hilbert space of loop quantum gravity. So this is the Hilbert space on the graph again. So you see that in some sense you can think, if you think that a manifold is discretized, or geometry as having little atoms of geometry, classically you can, for example, like see this as a Fock space, but all the atoms, all the particles of the Fock space are little atoms of geometry that you put together. So classically, this is just saying that, for example, the building blocks of this blackboard are these little squares that we put together. So classically, if I put many little squares together, I reconstruct this blackboard. So what we say in loop quantum gravity is that the quantum version of this tetrahedron is this intertwiner here. So classically, this is a tetrahedron, which is just a chunk, a piece of a discretized 3D manifold. But now quantum mechanically, we have to represent this with some quantum mechanical objects. So what are these quantum mechanical objects? They are just these angular momentum data, this SU2 quantum mechanical data. So in usual SU2 or angular momentum quantum theory, we have the same objects. We have these intertwiners that tell us how these representations are recoupled together. So here's the same thing. The intertwiner is the quantum version of the tetrahedron. So classically, the tetrahedron, they are the building blocks of the 3D manifold, which is discretized. And in the quantum theory, the intertwiners, they are the building blocks of the Hilbert space.
Can you have more lines on the same node?
Yeah, so you can.
Can you have 5?
Yeah, and if you have 5, what you're doing.
But if you have 3, can you have 3?
You cannot have 3, no. So if the.
So at least 4.
I mean, so it depends which manifold you want to see the graph dual to. So if you take a graph that has only 3, you can only see this as dual to a 2D manifold. You can never see it as dual to a 4D manifold. So if the ended manifold is d-dimensional, the valency of the dual graph has to be at least d plus 1. So here the graph is 2-dimensional, so the nodes have to be 3 elements. And here the manifold is 3-dimensional, so the graph has to be minimum 4 elements. But I can put like another one like this and another one. So then instead of having tetrahedron, I would do more complicated 3D polyhedron. So this is the idea, is that there is a discrete polyhedron that is encoded in these graphs. So just one last remark about these discrete geometries is that maybe you're familiar with what people call Reggie geometries. And Reggie geometries is something that is known, has been known for a long time in classical gravity. And Reggie geometry is just a way, it was invented by Reggie, and it's a way to discretize the Einstein-Hilbert action on a simplicial manifold. So the idea of Reggie was that, okay, we can simplify the equations of classical GR. I can just discretize the 3D manifold and then write down the action for GR, so the classical action, in terms of geometrical data. In terms of the length here, so this length L1, so the length of all these links, L1, L2, L3, and also the angles between all these spaces. So there is a well-defined way that is known to write down the Einstein-Hilbert action and the equations of motion, not in terms of the metric, but in terms of discretized version. See, because the metric determines the length of all these, of all the sides of the tetrahedron. So classically, we can do this through writing. And so there is a very precise sense in which the geometries of loop quantum gravity, they are more general than Reggie geometries. It was known, in fact, for what people tried at the beginning was to do quantum Reggie calculus. So to take these Reggie geometries and quantize them. And it turns out that this is not well defined, this doesn't work. And in loop quantum gravity, what happens is that we see that the geometries that we consider, they are more general than these Reggie geometries. And why they are more general? There is a precise sense in which they are more general. And the sense is that you see that the areas of these two triangles, they are the same. So we have tetrahedron here, then this link is dual to a triangle in this tetrahedron and a triangle in this tetrahedron. But what is imposed is only that the area of these two tetrahedrons be the same. But what we don't impose is that the shape be the same. So we relax, in fact, a condition that is present in Reggie geometry. In Reggie geometries, the shapes have to match. So you see that here the shape of this side of the triangle matches the shape of this one. Otherwise, we cannot glue them together. So in loop quantum gravity, we relax this condition. So we relax this condition of matching the shape of this triangle to the shape of this triangle. So in this sense, there is a bit more freedom. If you try to glue this tetrahedron together, you can put them side by side, but the shapes of the triangles do not match. Only the areas of the triangle will match, but not the shapes.
But what about time? Because in that case, time...
Yeah, for the moment there is a priori no time. For the moment. So now we can talk about dynamics and what happens to... So I just wanted to give you this intuitive feeling of what happens with these graphs. Because if you read them in a loop quantum gravity paper, you will see all these graphs everywhere. So now we can know that whenever you see a graph like this, you can think of this graph as being really a discretization dual to a discretized manifold. Exactly in this sense. So now we will see time evolution. What is the picture of time evolution? Or the picture of the dynamics with these graphs. And so the situation is the following. So now in principle what you have to do is to consider the quantum Hamiltonian constraint. So classically, the Hamiltonian constraint is the integral of x is the lapse function here. Is 1 over square root e. This is the f of the Ashtekar-Barbero connection. Plus 2 minus 2. this is the remaining constraint, the last constraint that we didn't impose. And we know that in the Hamiltonian theory, this constraint, its action like Poisson bracket on the basic phase space variable, is to evolve these variables into time. So into the slices of the ADM foliation of spacetime. So in principle, what we should do now we're going to turn this into a quantum operator. But of course, the way to turn this into a quantum operator, first we have to write it down in terms of variables that are used in the quantum theory. What we said is that there is no operator A hat in the quantum theory. So there is no operator for the connection. What we have instead is an operator or the holonomy of the connection. So this has an equivalent in the quantum theory. This doesn't happen. And same thing is that these electric fields E, they have no analog in the quantum theory. What we have is the flux of the electric field in the quantum theory. So the first step would be to rewrite this. So in terms of holonomies and fluxes. So this would be the first thing to do. And then once it's written down in terms of holonomies and fluxes, then we can turn it into a quantum operator. So there is a construction like this. It's I'm finding in the literature or in the lecture notes that I mentioned the first time. It's not very long to write it down, but it has lots of structure, so it's not very informative. So I'm going to tell you like how it acts, and then we're going to take a different point of view on the dynamics. Because it turns out that today, most of the people in quantum gravity, they don't work anymore with the canonical dynamics. Because it's a bit too complicated. This constraint is a bit too messy, and the way to regularize it has sort of like mathematical ambiguities. So I'm just going to tell you the result. So what it does, in fact, remember that what we have to do is to now act with this constraint on a state. So we take a spin network state, and we act with this constraint on a spin network state. And essentially, once we do this, so if we write this in terms of holonomies and fluxes, what we get is a quantum Hamiltonian constraint, which is a functional of the holonomies, of the fluxes, and of the volume operator. Just because the volume operator is a functional of the fluxes. So it turns out that there is a convenient rewriting of this. This is due to Thomas Tiemann. He found like all the tricks to write this down in terms of the volume and the holonomies. Then once this is done, you can transform this into a quantum operator. But what happens is that if you act with this quantum operator on a spin network state like this, what it's going to do is to create new links, of the graph, so new geometrical elements in some sense. So one can look at the action of this. People did this. They look at the action of the Hamiltonian constraint, and what they see is that the Hamiltonian acts on the nodes of the graph. If you act here on the link, nothing happens. You cannot act on the links of the graph. What happens is that the Hamiltonian constraint sees the nodes of the graph. And essentially, if you hit with the constraint a graph like this one, for example, what you're going to get is a new graph with new nodes and a new link. So you're creating this essentially. And then, of course, you're changing the labeling of the spins. Here you have spin J1, J2, J3. Here you have J1, J2, J3, J4, J5, J6. So just heuristically, if you want, this means that the action of the Hamiltonian constraint is really doing what we can think about quantum gravity, in the sense that it's evolving the states in time. Of course, here there is no like fixed notion of time, because this is quantum gravity. So already in classical gravity, there is no fixed notion of time because of diffeomorphism invariance. So when you go to the quantum theory, there's no time parameter in this sense. So there's no way to say that at each time this happened. There's no way to say that first I have this state of the gravitational field, then I wait 5 minutes, and then I have this other state. This we cannot say in a quantum theory like this. do this, we would have to deparameterize. So for example, put the Hamiltonian for the matter, and then do the same thing as in loop quantum cosmology. For example, use the scalar field as a time, and use the scalar field time to ask questions about time evolution. But so independently of this, you can just see this Hamiltonian as a constraint operator. This is a constraint, this term loop quantum operator, and this constraint acts on the states. Because it's written in terms of holonomies, fluxes, and volume elements, and all these things, they act on the spin network states. So if you act with the Hamiltonian on the spin network state, it's going to change the graph. This is very deep thing, in fact, that happens, because we saw that first we start with these spin network states, the graphs, then we impose SU2 gauge invariance. When we do this, we don't change the graph, in fact. We keep the same graph. What we do is just say that at the nodes of the graph, we have SU2 intercliners. Then we look for the diffeomorphism in invariant space, and again, we don't change really the graphs. What we say is that we can forget about the embedding of the graph on the manifold. But then the Hamiltonian constraint does something very different. This constraint changes the graph. This constraint is really graph changing. When we act on this, we get a new graph. So if we get a new graph, we get a new state of the gravitational field. So we get a new spin network state, so a new state of the gravitational field. We don't know the time that elapsed between these two states, but this is what the Hamiltonian constraint does. So now we are going to rewrite this in a much more sort of powerful way, and we will see, hopefully, even more clearly what happens to this geometry and what time evolution is. We will see. So the reason for which I don't want to say more about this Hamiltonian constraint is that now it's still a bit of an open problem in quantum gravity, because we don't know, in fact, really how to write down explicitly the kernel to this constraint. So there is no way of we know how the constraint acts in specific states, up to, there are some ambiguities here in doing this. But what we really don't know is to find an explicit way to write down the physical Hilbert space. So we cannot write down the Hilbert space and write down all the states, the generic form of any state that is in the kernel of this constraint. This we cannot do. What we can do is act with the constraint on some specific states. So for this reason, there is a more powerful way to write down the dynamics of the theory, and this is through the spinfold models. So we will see what the spinfold models do. And so you can think, so there was an early idea by Rovelli and Reisenberger was to see what we can do is now construct a projector that projects the states on the kernel to this constraint. So we take any state, we hit the state with the projector, and the projector puts the state in the kernel of the Hamiltonian constraint. And so this means mathematically that we can construct a projector like this. And this projector is a product over all these points of this delta function. This is a priori completely ill-defined because I'm taking an infinite product over all the points of a spatial manifold of delta function, delta distribution, a very complicated operator here. So this is really ill-defined. Formally, you can think formally what happens first. So now you can know that a Dirac delta like this, you can write it in terms of an exponential. So I can use sort of the path integral representation of the Dirac delta and write this as the integral for some n, dimension I, this h hat m is just the integral over the smearing of the lapse with the Hamiltonian constraint. So now the idea is to say that the physical inner product between network states, we take two states, S1 and S2, so two spin network states, or two kinematical states, and we want to know their physical inner product. We want to construct this physical inner product. So this is what we're looking for, an expression for this physical inner product. So what we know is the kinematical inner product. What we said what we constructed so far is the kinematic inner product. So we said that we have these network states, and these states are cylindrical functions, and on the space of cylindrical functions, we have an inner product which is dictated by the Haar measure on the group SU2. So this is a well-defined inner product. What we can do is just take this state and put it in the this projector on the kernel of the Hamiltonian constraint. And now you see that very formally what you can do is now expand this exponential. We write it like this. What we can do is write this physical inner product as this thing. So H. This is just sort of expanding this exponential in terms of series. And then people noticed that, okay, people heuristically wrote this formula down, and then they said, okay, but now in the canonical theory, so this H is the H of the canonical theory. But in the canonical theory, we have a well-defined regularization of this operator, and we know how it acts on these spinetral states. So here we're doing like an action of this Hamiltonian constraint on the spinetral states. But remember that whenever we act with the constraint on the spinetral state, we create new links and new nodes. We change the structure of the graph like this. So you can think of this, in fact, as being just the sum what we did is just formally write down this action, in fact. So first I have the term n equals 0. This means that I don't act on this state at all. I just take the kinematical inner product. Then I have the term n equals 1. This means that I have one part of the Hamiltonian, so I act only one time with the Hamiltonian on this state. And so this we could see in some sense. So remember that what the path integral is. A path integral is just a sum over all the histories of the system, over all possible configurations, states of the system that interpolate between the two boundary states. So this means that we fix boundary states, S1 and S2, and what we do is this sum, and for each of this sum, we assign a quantum transition amplitude. So I have this amplitude AN that we didn't define for the moment, and I wrote that this amplitude depends on some spins, label, and some interfinal labels. Because in the theory, this is what the data that we have. We have states labeled by spins and a bunch of interfiners. So we could think that whenever we act with the Hamiltonian constraint, we define amplitudes like this. So we can represent this geometrically to see what this means. This means that we can start with a state, this state. Imagine that the end state is this one. This is what we said. We said that in the canonical picture, if we act with the Hamiltonian in this state, we create a new link and new nodes, and we get this other state of gravitational. Now you can see that there is one way to interpolate between these two states. This way is to see this as evolving in time here. Now we have a linear vertex here. So you have this three-dimensional picture. So I put time here, but it's not really time again because it's quantum gravity, so there is no notion of time in which to measure this operation. So there is no clear way to say when the Hamiltonian constraint acted to create this node. But what happens is really this. You take this state and you evolve it, and then at some point the Hamiltonian constraint acts. And when it acts, it creates this vertex here. And then you have this other state. This is like the vertex of a quantum theory, the vertex of a QFT, the vertex of a Feynman graph.
Try that with the B here.
This is this vertex amplitude. This is what you see. You see that if we take a spin network state, we evolve the state in time. It's like this is a spatial slice. This is the analog of a discretized version of the ADM evolution, if you will. We have a spatial slice with a certain state, then we evolve this into time, then we have a final slice with another state in it. A certain slice with a certain configuration of the metric, and another slice with another configuration of the metric. And in between what happens, so the dynamics of quantum gravity happen in between, and what does the dynamics of quantum gravity do? It changes the state of the gravitational field. So it creates little quanta of space. This is what happens here. We have this vertex here, which is an action of the Hamiltonian constraint, and then we have this new state, which is a new state of the geometry, new state of the gravitational field.
Is it possible to destroy or?
And you can also destroy it. I think so. I'm not sure if you can describe it.
But you have to define the initial and final state, right?
Yes,
You would
yes.
have to know that a priori.
Yeah, you have to specify it. So now the role, the game, what you have to do is to try to define this amplitude, this vertex amplitude. But so now also heuristically you can see.
I know you have a doubt about the possibility of annihilation. Don't you have annihilation and creation operator?
Not in the usual QFT sense, in this sense. What you have is a Hamiltonian constraint that acts. I'm not sure about the details of its action. If you destroy nodes, you have certain problems related to divergences, and but it's not really like annihilation equation like in field theory. You don't have to structure it. But so now you can see that here I draw like a three-valent graph. So you can think, because of the correspondence that we gave earlier between the graph and the dual geometry, you can think of this graph as being just, for example, there is a triangle here. This triangle is a little building block of this two-dimensional slice. And now we have another state which is more defined. Which is fine. And then you see that you can also put the dual objects for this vertex here. You see that this vertex now is exactly 4-valent. So why is this vertex 4-valent? So 4-valent means that there is a tetrahedron here. This is exactly a complete picture of a discretized 3-manifold with 2 boundaries, if you want. So we have this 3D manifold here. So in the bulk, the entire manifold, it's 3D, so it's discretized with tetrahedron. And now on the boundary, so the boundary, the two slices are 2-dimensional slices. So on these slices, discretization is with triangles like this. So I have a certain graph here, a certain graph here, and something in between in the middle. And so in some sense, this vertex amplitude is the amplitude for creating, in the quantum theory, a new tetrahedron. So we said that it's more convenient to write this down in terms of these graphs, so I can talk about the vertex amplitude, to create a vertex, but you have to think of this vertex as being just a mathematical representation of this tetrahedron. This vertex amplitude is the quantum amplitude for creating a tetrahedron. So I have a certain state. So gravitational field is a quantum geometry. This quantum geometry is little discrete building blocks of geometry interacting together. Now we evolve this state, and I go to another state of the gravitational field. In between, I change the state of the gravitational field. So by this, what we mean is that we change the state of quantum geometry. We add or we remove or we move around the structure of these little building blocks of space-time. What we would like is a way to concretely see how this happens. Can we really see this construction? For the moment, it's very formal. At the moment, the only thing that we constructed rigorously was these states, so these kinematical spinetron states, so these boundary states of this theory, and then we wrote down this very naively and hand-wavingly, and I said, okay, there's an amplitude, and this amplitude corresponds to this process. Now what we want is to see this mathematically, to really construct this thing. And so, the most simple way to construct this is first in 3 dimensions. This is in fact how spin-fold models were introduced. It was in 3 dimensions. Yeah, so by the way, this is now called a spin-fold model. So this thing here would be a spin network. Because it's a network of spins, and this is a spin foam, because it's just a foam like with bubbles of spins. So in the bubble here we have a spin foam. So in fact, what it means to define a spin-fold model, the mathematical definition of a spin-fold model is the following. So, give me, for example, a 3D manifold. 3D manifold M. What I can always do is chop the manifold, decompose the manifold into little building blocks. You can always do this. Give me a 3D manifold, and you can choose discretization. Then you choose discretization, and let's call it delta. So delta, discretization delta, for a 3D manifold, it has tetrahedrons, we call them tau. Then you have the triangles, T, and you have all these links. L. So these are the building blocks of a triangulation of a 3D manifold. So now what we said is that it's more convenient to work in the dual picture. Instead of writing down this, what you can work in is the dual picture. This triangulation dual. This means that instead of having a tetrahedron, I just consider a vertex V. Instead of having a triangle, I have an edge E. Instead of having a link, I have a face F. It's just a completely equivalent way, but it's more convenient to work in this representation. So usually spin-fold models are written in terms of these objects and of this one. It's completely equivalent. These are correspondence. The point is precisely this one. You see that I have the vertex of the dual discretization, and this vertex is dual to tetrahedron. So if you give me the black structure, it's the same thing as if you give me the blue structure. So the discretization or the dual discretization, it's the same thing. So the thing is that, okay, you take a 3D manifold, for example, and you choose discretization, then what you do is you assign to the vertex, to the edges and to the faces, a certain set of amplitudes. And you define an object on a triangulation delta like this. So a product over all the faces delta star of face amplitudes, product over all the edges delta star of edge amplitudes, and product over all the vertices of vertex amplitudes. This is the definition of a spin-fold model. You take a 3D manifold or any dimensional manifold, 3D or 4-dimensional, then you discretize it, and on the discretization you define amplitudes. And now how do you define these amplitudes? You define them in the group theoretical data. And what is this group theoretical data? You can understand now from what we know from the spin network states. We know here that the links are labeled by spins, and that the node is labeled by an intertwiner. So you see that, imagine that now when I evolve this in time, see that this intertwiner is now becoming this edge of the spin form. This intertwiner is like now spanning this edge. Now this edge is labeled by this intertwiner. And now this link here is forming now a face here in the bulk. So now this face here, this entire face, is labeled by this spin j. We have also a face here. I have another face here, a face. So here we assign spins to faces and intertwiners to the edges. And now you see that the vertex has to depend also on, so the vertex amplitude, AV, has to depend on some data. And what does it depend on? It depends on all the incoming data. Then this vertex knows about the intertwiner that is arriving here, and the spins labeling all the faces that arrive here. So just to say that this is going to depend the functions of this amplitude is a functional of the spins carried by the faces, product over the edges. Edge amplitudes. This vertex amplitude depends on the spins. And on the edge, I also put the dependency on the spins of the faces. If you see that this edge here, also this intertwiner has to be compatible with the spins labeled by these faces. In the same way that this intertwiner here is compatible with the spins labeling these links here. But anyway, this is just to tell you what the structure is, what we want to construct. What we want to be able to do is to take a 3D or 4D or 5-dimensional manifold, then discretize the manifold, and then use group theoretical data, so spins and intertwiners, and then assign this data to all the pieces of the manifold. Then once we do this assignment, we construct an amplitude. And then what we claim is that this amplitude is a path integral for gravity. That this z of delta is a regularized or a discretized version of the path integral that we want to write down for quantum gravity. So now, to give you a complete construction, we can do this in 3 dimensions. 3 dimensions, this can be done exactly, explicitly. This is in fact how it was introduced first, historically.
But if this is just a model, so there should be another way to do the evolution. It's just a model, right? You should have another.
Yeah, so now what I have to specify is really the form of these amplitudes. So I have to write down amplitudes that are compatible in the sense that I have to define with the dynamics of quantum gravity. So I cannot, if you give me like...
Okay, this structure is from the theory, but the model is encoded in the amplitudes.
Yeah. Yeah. So this is if you want a spin foam, and choosing these amplitudes is a spin foam model. Now what you have to find is a prescription that tells you what is the shape of this amplitude, the shape of this one, the shape of this one. And now we have to think about how to guess, how to find these amplitudes. So the motivation for writing down such a model was this one. The motivation was that we have these kinematical states that we constructed rigorously. If we think of them as doing a path integral evolving in time, we think of this covariant path integral picture, it's equivalent to gluing all these amplitudes together. Because we have this dual geometry, this discretized manifold, and then we assign amplitudes to all the building blocks of the discrete manifold. But you can see that in 3D, it's exactly what happens. In 3-dimensional, this construction is completely rigorous and understood and under control. So in 3 dimensions, this is really the way to write down 3D quantum gravity. So 3-dimensional quantum gravity is really written in terms of these spin-form models. You see why? What you can do is look at the 3D gravity. Sorry. So in 3 dimensions now, we take a 3D manifold. So we have, of course, usual Einstein-Hilbert action for gravity. This is not very convenient. If you try to quantize with this action, you can do derivative computations or things like this. But you have other formulations of 3-dimensional gravity. So just like in 4D, we also have the Hilbert-Palatini formulation. So we have a formulation in terms of a connection and a triad, and then the action is just the following. So it's essentially like this. The action is just E wedge F. Remember that in 4D, the Hilbert-Palatini action was star, so Hodge dual of E wedge F. Here the action is just E wedge F. So this is just, if I put the space-time indices, d3x, epsilon mu rho. This is the action for 3-dimensional gravity. Now if you want, we can do a 3+1 decomposition. We can do ADM or a canonical analysis of this. So I split space-time between space and time. And then I split these indices between, so you see first I have epsilon 0, AB, E 0, I, and B, plus 2, 0. So what I did is just to expand this sum over all these indices. So mu there were 3-dimensional space-time indices, so there's no time-like indices and one time direction and 2 space direction. So I can just expand this, and by doing this I get immediately the Hamiltonian form of the action. I mean, almost, because I can define this. And then what we usually do is the following. So you see that I have this term here. So 2. So are you familiar with this, or should I do it? I do it just fine. So I'm just writing down this term. AB. Fi E0. And this is just 2 epsilon AB. E0 plus E0. Omega AB plus epsilon IJK. So why do we do this? Because you see that there is a 0 component here. This means that there are time derivatives in these components of the curvature. So because there are time derivatives here, this is here that the canonical term is hidden. Because if you want the Hamiltonian, you have to write down the Lagrangian as PQ dot minus the Hamiltonian. So we have to find where the time derivative is hidden, where the Q dot. You see that the time derivative is here. So in fact, this can be written, this is the canonical term here, omega dot, and then the rest, this, you can do an integration by part here, put the derivative on the E, and then you can take this omega 0 also in the front, and put the E in this commutator, and what you get is the Gauss constraint. So what you get out of this is just EAI omega I0 GI for E to epsilon AB this is just sigma This is just now the Hamiltonian form of the 3D action gravity. So what really is very simple. You just do a few steps and you get immediately to the Hamiltonian form of the action. So this means that now, see there are two constraints. I0 is a Lagrange multiplier. There's no momentum conjugate to EI0, and omega 0I is also a Lagrange multiplier. And so these two, they enforce the constraints of the theory. And the first one is the Gauss constraint, and the second one is the flatness constraint. And so this constraint tells you that erase here. I will erase this thing. So we're going first. I'm telling you why three-dimensional gravity is so simple in some sense, and why it can be solved explicitly. In fact, if you do the full constraint analysis, you can see that there are no more constraints. These are the two first-class constraints, and there are no any other constraints. So now we can count the degrees of freedom. You see that you have so this is 3 times 2 variables, so 6 variables. This is 6 plus 6. This is 12. And this is 3 constraints, because you have only one index I. This is also 3 constraints. This is a total of 6 constraints. And now the physical degrees of freedom. So it's a 12. So the unconstrained phase-space variables minus the constraints, but these are first-class constraints. So remember that we have to count them twice, because there is one algebraic relation between the E and the omegas, and then there is one relation because of the orbit generated by these constraints, because of the symmetry generated by the constraints. And the degrees of freedom is 12 minus 6 times 2, so it's 0. So this tells you that three-dimensional gravity has 0 degrees of freedom. So in 3D gravity, there are no. This is a statement. Sometimes you hear that there are no gravitons in three-dimensional gravity. So there are no local propagating degrees of freedom because of this calculation, essentially. So remember that when we did this in 4 dimensions, in the first lecture, what we found was 4. And the 4 in 4 dimension is the 2 polarization of the graviton and the 2 conjugate momentum, which means that you have graviton, you have local degrees of freedom. Here you find 0. This means that there are no propagating degrees of freedom. So there are only topological degrees of freedom. It means that this theory just depends on the topology of the manifold that you choose. And you'll see that this, in some sense, is responsible for the fact that three-dimensional gravity is so simple and so easy to quantize. It's not that easy because there are many complicated mathematical structures involved. But apparently, because of this, it's completely trivial. Nothing happens. But now what we can do is, so take again this action, E omega, this was E I Fi. Now we can try to define a path integral for this. Now we can define this path integral. So Z, the manifold M, E omega, E I S. We can try to do this here. And now what I'm saying is that first now let me discretize the theory. Instead of computing this path integral, we can discretize the theory. Or, roughly speaking, you can already see what is going to happen. You can see that the reason for which we can compute the path integral for 3D gravity is that, look at its shape in fact. This is just, so I can integrate over E in fact. E is just a multiplier enforcing that F be vanishing. So I can integrate already over E, and what I get is a delta function of F. This is telling you that in 3D gravity, these configurations are the configurations for which the connection is flat. So F is equal to 0. So the curvature of the connection is 0. So to make contact with this, it's not nice to do it like at this level. It's first nice to do a discretization. And how to discretize? You can do the same discretization as we did in loop quantum gravity, in the canonical theory. What we can do is replace, remember that E now, so E is a one form. We can replace it by, we call this XF, and why I call it XF? Because since E is a one form, I can integrate E over one-dimensional submanifolds. And these are precisely these links. So now I choose a triangulation of the 3D manifold. In this triangulation, I have all the links of the tetrahedron. And then I say, okay, on all the links, I integrate this triad. Then this gives me an element that I call XF. I could call it XL, but I'd rather call it XF. So I call it XF. Because L is dual to the face F. Okay. This is an element in the Lie algebra again. So since this is a Riemannian 3D gravity, the gauge group is SU2. And now omega I'm going to replace omega by replace omega by its holonomy. Now what you can define, what you have to discretize is not the connection, it's the curvature of the connection, so this F here. So now we have discretization of the field. It's just given by this Lie algebra element, XF. What you have is to discretize the curvature. But again, as in gauge theory, the way to discretize the curvature is to just compute the holonomy of the curvature around a certain cell. But if I want the curvature of the holonomy around the face F, so you see now that see what happens in the dual picture. All these faces F, they are bounded by these links E. The links around the face are the links E. So what I can do is take define a new element, which is GF, which is the product like this, over all the edges belonging to the face, the element is E. So whenever in this dual complex here, in this dual decomposition, I have a face. Whenever there is a face like this, with a certain orientation, I can compute the holonomy G1, G3 along all the edges around the face, and then take the product of these holonomies. So this gives us the face holonomy. So the holonomy of the connection around the face. And this holonomy of the connection around the face is discretization of the curvature, in fact. What we're doing is discretizing the variables on the discrete data that we have once we choose the triangulation. Now what you can define is the discrete action. The discrete action is just now S, which is a function of E, H, G. H. Is given by the trace in SU2. Sum over the faces. So it can seem a little strange to you because we're using the dual decomposition. So we're using the faces F of delta star. It's not really straightforward to see what we're writing down. But what we're writing down is essentially we took this curvature, this term EF, and discretized this in terms of all the faces of the dual convex of this thing here. So these faces are the faces here. These faces here. I will remove spin from here, but this face here. So you see that this is what we said. On this picture we have two-dimensional objects. You have the triangles, which are the blue triangles here, which are the boundary of the tetrahedron, and you have the faces. And these faces, they live in the dual decomposition of these faces. So what we just say is that the way to discretize this action for three-dimensional gravity is to write the curvature in terms of this product of holonomies, and this is the discretized version of the integral of the action. So now what we can do is really compute the path integral. And what we can compute is path integral of a certain discretization. What we did is we just took the exponential of I times the discretized action, and we integrate over all these one-dimensional fluxes and over all these holonomies. And these holonomies, they are group elements. So we integrate over SU2 with the SU2 Haar measure, and these fluxes are the algebra elements. So we integrate with the usual Haar measure of the algebra. The algebra is like R3. So we can just use the like measure here. Now you see that now we can integrate over these fluxes, over this XF. Same thing as we did before. We said that we could integrate over the triad, get the delta function of the curvature. Now we can do the same thing. We can integrate over these fluxes here, and then we're going to get, so only this product remains. Integral over SU2, product over the edges of the HE. Then we have a product over the faces of the delta function of the face holonomies. So you see that what is the physical content of this? The physical content of this is that what we are saying is that we took the manifold, the three-dimensional manifold, we discretized it. So in this discretization we have a tetrahedron, triangles, links. We have a dual discretization. And what we're saying is that the physical content of this is that on all the faces of this dual decomposition, so on all these faces, the connection is flat. So the curvature is 0. And the curvature being 0 means that we have a delta function of the holonomies. So remember that this is delta function on the group SU2. So on the group SU2, these holonomies are, this means that it's not equal to 0, it's equal to 1. Because it's a group element. So this delta function is imposing that this holonomy be equal to 1. So you see that if the holonomy of the connection around this face is equal to 1, this means that the connection is trivial. See what happened in gauge theory. So when the connection is flat, so when the connection is such that its curvature is equal to 0, it means that the holonomy of the connection is trivial. So the holonomy around the face like this is the identity. What we're imposing here is a product of delta function imposing that the holonomy of the connection be the identity in all the faces. So this means that you see that we have discretization, and what we are imposing is that the theory is flat everywhere. And what is this flatness? This flatness is the topological nature of 3D gravity. Because we saw in the Hamiltonian that there are no local degrees of freedom. What we saw is that we have two constraints. One of the constraints is the Gauss constraint, SU2 gauge invariance, and the other constraint is the flatness constraint. The other constraint was f of omega equals 0. This is one of the constraints of three-dimensional gravity. And the reason is that the theory, the connection is flat. So why? The reason for which we are writing everything in terms of this can seem like completely unnecessary and fancy, but the reason for which we want to do this is that we want to see the structure emerging. We want to write this as a spin-fold model. And once we understand this, we're going to understand in 4 dimensions how we can reproduce the same thing. So now yes, let's do a break maybe. Break.